Hello everyone. Today I will be presenting Sarathi-Serve. In this work, we explore the latency throughput trade-off in existing LLM serving systems, and we see how we can address this problem. This is joint work between Georgia Tech and MSR India. Now, in the past couple of years, there has been a meteoric rise of large language models, and as a result, these have become one of the most significant compute workloads today. Consequently, there has been a lot of interest from the systems research community towards improving efficiency of LLM serving. In fact, in the last 2 years, we have managed to push the throughput boundaries by 20 to 30x higher. However, having good throughput is not sufficient for production LLM serving. We also need to get low latency. In this work, we first try to answer if existing serving systems can maintain low latency with high throughput. I call Nitin to present us a small demo.
Yeah. Hi everyone, I'm Nitin. I'm going to show you how VLLM, a state-of-the-art LLM inference scheduler, behaves when we interact with it with and without load. I've already started the server in the background. It's booting up. We are running Llama 370 billion on H100 DGX. We're now going to ask VLLM to generate some code snippet. As we can see on the left-hand side, that it's very fluid output token generation. It's fast. Without loads, everything is great. Now, will it be the same when we add some background load to it as in the production case? I have a script for that. I am running that script to generate additional requests in the background. The server is getting those requests. Now, when we ask VLLM to generate the code snippet, you can see that there are several instances where the output pauses. You can see them when the red counters come up. There are a lot of them, and this is what we call a stall. Whenever there is a stall, the user doesn't know, has the request completed, what's going on with the system. It's not something that we want in a production system. And also you can see the time to complete the request is too high. Compare it to the without load scenario that we just showed. It's still like in the early stages of this code snippet generation. I will hand over back to Amey to talk about more about these problems and how to solve it. Thank you.
Thanks, Nitin. So, as Nitin showed, existing serving systems make a very severe latency throughput trade-off when, even though they can serve with high throughput, the latency becomes so high that these systems become unusable in production situations. Now, in rest of this talk, we will first analyze why this latency throughput trade-off occurs in the first place, and then we will present stall-free batching, where we address this trade-off using arithmetic intensity, slack, and decodes. And finally, we will present some key results and their analysis. Let's begin by understanding the latency throughput trade-off and what causes this. So we will begin by some fundamentals of LLM inference serving. So when a user sends a request like is tomato a fruit, all of these prompt tokens are bashed together and passed through the model, and this whole process happens in a single forward pass of the model. This is called prefill. Subsequently, each decode token is generated sequentially, one at a time. This is called decode. And prefill phase has high degree of parallelism due to clubbing of several of these prefill tokens together. However, decode phase is inherently low on GPU utilization and because of the sequential processing. Now, this raises a natural question of how we can improve the throughput during the decode phase. Well, this is done using batching. Essentially, requests from several distinct users is clubbed together in a single batch and processed. Let's see how this works. So consider at time t equal to 0, we have two requests, A and B, enter the system. Now we can process the prefills of both of these requests first. And now, once the prefill for both of them is done, we can now start doing batch decodes of both of the requests together. Essentially, by batching these two requests, we have doubled the throughput of decode phase. In fact, the efficiency of decodes increase almost linearly with batch size. And this has been the key driving force behind increasing throughput in LLM serving systems. However, there is a problem. Consider the situation where we have decode for 2 requests A and B already running, and now 2 requests C and D enter the system. Here, we have a choice to make, whether we should continue with the decodes of existing requests or should we schedule the new request first. So in option 1, let's say if we first schedule the prefills of the new request, we can do batch decoding of all the 4 requests together. This helps increase the system throughput significantly. However, this leads to increase in latency or decode stalls for request A and B. Alternatively, other option could be to finish the decodes of existing requests and wait till the system is in an idle state. And at this point, we can schedule the new prefills. In this case, we don't have any decode latency stalls. However, the system throughput goes down due to low batch sizes. The first type of schedule can be called prefill prioritizing, and it is used by systems like VLLM to increase the system throughput. Whereas the other schedule can be called decode prioritizing, and it is used by older systems like faster transformer. Now, in summary, we have this stark latency throughput trade-off in existing LLM serving systems, where systems like faster transformer have a low latency, but they also have very low throughput. With all the systems optimizations, we have managed to push the throughput boundaries much higher up, but at the same time, the decode latency has also gone up. Ideally, we want a scheduling policy which can achieve both high throughput and low latency. This is where Sarathi-Serve comes into picture. In the rest of this talk, we will understand how Sarathi achieves this. So let's go back to the original scheduling conundrum. One alternate option here could be to fuse the computation of request C, like the prefill of request C, along with existing decodes for request A and B. Let's see how this plays out. This is called mixed batching, and this was originally used in a system called Orca. The idea here is to fuse the computation for prefill and decode together. However, the problem is that naively combining prefill and decode and batching them together doesn't help in solving this latency problem. In fact, we see that even for batch size of 64, if we add a prefill to this decode batch, the latency goes up by 5x. Let's consider the scenario where we have decode latency SLO of 10 seconds. In the baseline prefill prioritizing schedule from VLLM, let's say we had decode for request A ongoing. Now we were under the latency SLO. But as soon as a new prefill request comes in, the prefill decode interference leads to a significant increase in decode latency, and we miss the SLO. Now, the same situation, we can see how it works with Orca and mixed batching. Even though the prefill and decode for B and A requests are fused together, we still end up missing the latency SLO because the latency of this micro batch is primarily dominated by prefill of request B. This brings us to our key insight that prefill computation can be done at a marginal cost if batched correctly with care. So we will now do some analysis of compute characteristics of LLMs. We will use arithmetic intensity as a vehicle for this analysis. Arithmetic intensity is essentially the amount of math operations done per byte of data fetched from memory. Here we have the arithmetic intensity as a function of number of tokens in the batch. When we have high enough arithmetic intensity, we operate in a compute-bound regime, and this is usually desirable. On the other hand, if we have low arithmetic intensity, we are essentially memory-bound. And in this scenario, the latency is primarily dominated by the time it takes to fetch model parameters from HBM memory to GPU compute cores. And as a consequence of this, the latency is largely independent of number of tokens in the batch and only determined by the time it takes to fetch the weights. On the other hand, in the compute-bound regime, the latency increases linearly with number of tokens. In prefill iterations, we have a lot of tokens, and thus we operate in compute-bound regime, Whereas in decode iterations, due to memory constraints attached with the decode phase, we operate with very small number of tokens in the batch, and we have very low arithmetic intensity. Sarathi-Serve constructs these balanced batches where we have enough compute, enough arithmetic intensity to saturate the compute, but at the same time, we don't take a significant latency hit. This brings us to the core policy and mechanism of this work, which is stall-free batching with chunk prefills. So the key idea is to split large prefills into smaller chunks that are just enough to saturate compute in decode batches. And this way, we can completely avoid any stalls for decodes while doing the compute in background for prefills in free. Let's see the same scenario again, where we have the VLLM schedule where we alternate between memory-bound decode phases and compute-bound prefill phase. In case of Sarathi-Serve, essentially the large prefill for request B is chunked into smaller pieces such that we can construct these mixed batches with request A and B together, which have latency similar to decode-only batches, but we are also able to proceed with the partial computation of request B. And these are memory compute balanced batches that lead to almost uniform inter-token latency. And that way, we can always achieve the TBT latency SLOs. Now, Nitin will show us how Sarathi performs under additional load.
Hey, hi again. What I am going to do is now side-by-side compare VLLM and Sarathi-Serve with the same example of generating a code snippet. The model, the setup, and all the background load remains the same. You are going to see VLLM on the left-hand side and Sarathi-Serve on the right-hand side. Right off the bat, you see that Sarathi is progressing very fluidly. It's like there was no background load. But the fact is that both of these are serving the same load. VLLM is experiencing stalls, and it is frequently hamstring, while Sarathi is smooth, it's predictable, it's what we want in production. We can actually see that Sarathi already finished, and this is a very nice high throughput, low latency trade-off that we are able to do with Sarathi-Serve that was not possible previously. I will now hand over back to Amey to talk about more quantitative evaluations of Sarathi-Serve and summarize our talk. Thank you.
We have seen how Sarathi performs and the user experience that it can provide. Now let's look at some numbers. Before diving into the numbers, we would like to first introduce some common performance metrics that we are going to use for evaluation. So there are two latency metrics that we care about. First is time to first token, which is the amount of time it takes for the first output token to show up after we send the request, and time between tokens, which is the inter-token latency. Given these two latency constraints, we want to maximize the QPS that can be served by the system. This is called system capacity. Higher system capacity leads to low serving costs. So ideally, we would want to optimize serving capacity as much as possible. So let's look at how Sarathi fares in terms of system capacity compared to existing works. In favor of brevity, here we are only showing results for ShareGPT-4 on A100 GPUs. You can find more results in the paper. We are evaluating under two latency constraints, strict and relaxed. Note that we can adapt the chunk size in Sarathi-Serve to address these different latency requirement scenarios. We can use a larger chunk size when the latency constraints are more relaxed, and we can use a smaller chunk size when we have strict latency constraints. We see that for popular models like Llama 70B and Falcon 180B, we can achieve through capacity gains up to 5 to 6x compared to existing serving systems. In summary, we demonstrated the problem with latency throughput trade-off in existing serving systems. We then presented a key insight around arithmetic intensity slack in decode iterations and how we can use them to perform prefill computation at a marginal cost. We showed key results and identified that Sarathi can achieve up to 6x higher throughput. And finally, Sarathi has been adopted in several open source LLM serving systems, as well as some proprietary offerings. You can use Sarathi today in VLLM, TensorRT LLM, DeepSpeed, and several other packages. You can also find our paper and code by scanning these QR codes. Thank you.